Welcome to the video on CS801, Internet of Things, focusing on the RGPV 8th semester syllabus. We will cover the top 20 most important questions and their answers, based on previous year question papers from 2022 to 2025. Unit 1 covers the foundations of IoT. Key topics include defining the IoT ecosystem, explaining the IoT reference architecture, differentiating IoT versus M2M, and detailing IoT enablers and design principles. Unit 2 focuses on hardware for IoT. The most important questions relate to sensors, actuator characteristics, RFID principles, WSN and its relation to IoT, embedded platforms like Arduino versus Raspberry Pi, and microcontroller interfacing. Unit 3, IoT protocols, is crucial. Questions frequently cover the IEEE 802.15.4 protocol, Zigbee architecture, and application protocols like MQTT, COAP, and AMQP. The role of IPv6 in constrained networks is also significant. Unit 4 addresses IoT security and risks. Focus on security concerns, different types of vulnerabilities, application layer attacks, modes of attack, and security models, including centralized and decentralized approaches. Unit 5 covers IoT applications. Key questions involve designing smart home architecture using Raspberry Pi, applications in home automation, and smart city concepts, including streetlight case studies, health monitoring, and smart retail. This slide summarizes the final list of 20 high-priority questions compiled from all units for optimal preparation for the 2026 exam. We now begin with the detailed answers for the most important questions from Unit 1, Foundations of IoT. IoT is a network of physical objects embedded with sensors and software for connecting and exchanging data over the internet. The ecosystem transforms raw data into actionable insights through sensing, connectivity, data processing, and a user interface. M2M communication is direct, point-to-point, and uses proprietary protocols on a limited scale. IoT, however, is massive, global, and uses standards-based IP protocols like MQTT and COAP, integrating data for cross-domain analytics. The IoT reference architecture is a layered framework for design. It includes the physical perception layer, the communication network layer, the middleware/support layer for intelligence, and the user-facing application layer. Key design principles ensure functionality and commercial viability. Data enrichment involves contextualization, aggregation, and value addition. Affordability focuses on low power consumption, hardware optimization, and scalability for mass deployment. Moving on, we start with the answers for the most important questions from Unit 2, focusing on IoT hardware. Sensors detect physical variables and convert them into signals. Analog sensors produce continuous signals requiring an ADC, while digital sensors produce discrete data with internal conversion. They are crucial for data acquisition and control in IoT. IoT uses various sensors like temperature, humidity, pressure, motion, light, and gas sensors. These devices are essential for collecting real-world data and are classified as either analog or digital based on their output signal type. RFID, or radio frequency identification, uses electromagnetic fields to automatically track tagged objects. It provides a unique digital identity, or EPC, for every object, enabling automated processes like supply chain tracking and access control. Arduino is for simple hardware prototyping and control, running a single sketch. Raspberry Pi is a full single-board computer running a Linux OS. It serves as an IoT gateway for complex tasks, data processing, and protocol translation. Embedded systems use interfaces like GPIO for basic on/off control, I2C for connecting multiple sensors with 2 wires, and SPI for high-speed communication using 4 wires. The selection depends on speed and device count. Actuators convert electrical signals into physical action. Key selection criteria include low power consumption, fast response time for automation, high accuracy for precision systems, and easy control capability via PWM or digital signals. A wireless sensor network, or WSN, is a network of sensor nodes that collect environmental data locally. WSN provides the sensing layer, while IoT adds global connectivity, processing, and intelligent services to that data. We now begin with the detailed answers for the most important questions from Unit 3, focusing on IoT communication protocols. IEEE 802.15.4 defines the operation of low-rate wireless personal area networks. It is the foundation for protocols like Zigbee, providing low-cost, low-power physical and MAC layer functionalities for constrained devices. 6LoWPAN is an adaptation layer that enables the efficient use of IPv6 over low-power 802.15.4 networks. It achieves this by compressing the large IPv6 header and fragmenting packets, making the internet accessible to small, constrained devices. MQTT is a lightweight, publish-subscribe protocol using a central broker. Its small overhead and asynchronous nature make it ideal for high-latency networks, ensuring reliable delivery even when connections are unstable. COAP is the specialized web transfer protocol for constrained IoT nodes, acting as a lightweight version of HTTP over UDP. It uses a request-response model and is optimized for low memory and power environments. Zigbee is a protocol built on 802.15.4. It creates networks using coordinators, routers, and end devices, supporting star, tree, and highly reliable mesh topologies. This flexibility is ideal for large-scale automation systems. RPL, or Ripple, is a routing protocol for lossy IPv6 networks. It builds a destination-oriented directed acyclic graph, or DODAG, allowing constrained nodes to efficiently route data toward a root gateway while adapting to unstable links. AMQP is a heavyweight, queue-based messaging protocol designed for reliable enterprise communication. It uses exchanges and queues to ensure secure and guaranteed message delivery, suitable for back-end IoT platforms. The main difference is complexity and use case. MQTT is lightweight and simple, ideal for constrained sensors. AMQP is complex and heavyweight, preferred for enterprise messaging that requires high reliability and flexible routing. Both protocols are essential application layer components in IoT. MQTT excels at the device level due to its efficiency, while AMQP handles secure, reliable message routing in complex backend systems. We now begin with the detailed answers for the most important questions from Unit 4, focusing on IoT security and risks. IoT security protects connected devices and networks. A major threat is denial of service, or DOS, which overwhelms a target with traffic. In IoT, devices can be targeted or used as weapons in a distributed attack, like the Mirai botnet. Application layer vulnerabilities arise from insecure software or data handling. Attacks include SQL injection for database manipulation, session hijacking to steal user identity, and cross-site scripting that injects malicious code into web interfaces. 5.509 certificates and encryption are the trust anchors of IoT. 5.509 verifies device identity using a certificate authority. Encryption scrambles data using algorithms like AES, ensuring privacy and integrity through digital signatures. Centralized models rely on a single server, offering simplicity but a single point of failure. Decentralized models, often using blockchain, distribute trust across many nodes, enhancing reliability and scalability but sacrificing speed. We now begin with the detailed answers for the most important questions from Unit 5, focusing on IoT applications. A smart home uses a Raspberry Pi as a central hub, managing sensors like DHT22 and PIR, and actuators like relays. Communication uses lightweight protocols like MQTT, allowing the hub to automate tasks like lighting and security based on local logic. Smart city streetlights are an IoT application that connects lamps to a central system via a mesh network. Key features include remote control, energy monitoring, automatic fault detection, and adaptive dimming based on motion detection, saving significant energy.